Welcome to Shri Learning Academy. Let's simplify signals in Unix and Linux. When we talk about inter-process communication in Unix and Linux, we have already seen mechanisms like pipes, message queues, and shared memory. All of those allow processes to exchange data in a structured way. Now we come to another very important concept that works a little differently. This concept is called signals. Signals are not mainly about sending large amounts of data. Instead, they are about sending notifications. You can think of a signal as a short message that tells a process that something important has happened and that it should react. To understand signals in a simple way, imagine you're working in an office with headphones on. You are deeply focused on your work. Suddenly, the fire alarm rings. You immediately stop what you are doing and react. The alarm does not tell you all the details. It simply tells you one thing: something important happened and you need to respond now. That is very similar to how signals work in Unix and Linux systems. In technical terms, a signal is a software interrupt delivered to a process. It is generated by the operating system, by another process, or sometimes by the process itself. When a signal is delivered, it interrupts the normal flow of execution of that process. The process then takes some action based on the type of signal and how it is configured to handle it. Signals are deeply connected to topics we have already covered, especially processes and system calls. A signal is always sent to a process, which we already know is a program in execution. The operating system keeps track of processes using process IDs. When a signal is sent, it is sent to a specific process ID. This fits naturally into the process management concepts discussed earlier in this module. Let us look at a very common example that almost every Linux user has seen. Suppose you are running a command in the terminal and it seems stuck. You press Ctrl+C. What actually happens here is not magic. When you press Ctrl+C, the terminal sends a signal called SIGINT, which stands for interrupt signal, to the running process. When the process receives SIGINT, the default behavior is to terminate. That is why the program stops immediately. This example already shows two important ideas. First, signals can come from the keyboard through the terminal. Second, signals have default behaviors. Every signal in Unix and Linux has a predefined default action. Some signals cause the process to terminate, some cause it to stop temporarily, some are ignored by default, others cause a code dump, which is mainly useful for debugging. Another common signal is SIGTERM. This signal is used to politely ask a process to terminate. When you use commands like kill without extra options, you are usually sending SIGTERM. The idea is that the process gets a chance to clean up before exiting. For example, a server process might close network connections or save data before shutting down. This is different from SIGKILL, which is a much stronger signal. SIGKILL immediately terminates the process, and the process cannot ignore or handle it. It is like cutting the power instead of asking politely. Now let us talk about where signals come from. One source is the operating system itself. For example, if a process tries to divide by zero, the OS sends a signal called SIGFPE, which stands for floating point exception. If a process accesses invalid memory, the OS sends SIGSEGV, a segmentation fault signal. You have probably seen messages like segmentation fault when programming in C. That message is directly related to signals. Another source of signals is other processes. A process can send a signal to another process using system calls like kill. Despite its name, kill does not always kill a process. It simply sends a signal. What happens next depends on the signal type and how the receiving process handles it. This again connects back to system calls, which we discussed earlier as the controlled way for user programs to request services from the operating system. Signals can also be sent by the same process to itself. This might sound strange, but it is useful in some cases. For example, a process might detect an internal error and raise a signal to trigger a cleanup routine or to terminate in a controlled way. Now let us focus on how a process reacts to a signal. There are three main possibilities. The process can take the default action. It can ignore the signal, or it can handle the signal using a custom signal handler. The default action is what the operating system defines for that signal. For example, the default action for SIGINT is to terminate the process. The default action for SIGSTOP is to stop the process temporarily. Stop processes can later be resumed using another signal like SIGCONT. Ignoring a signal means the process tells the OS that it does not want to do anything when that signal arrives. Not all signals can be ignored. For example, SIGKILL and SIGSTOP cannot be ignored. This is a design decision to ensure that the system always has ultimate control over processes. The most interesting option is handling a signal. Signal handling allows a process to define a special function that runs when a specific signal is received. This function is called a signal handler. When the signal arrives, the normal execution of the process is paused, the handler runs, and then the process may resume execution. Let us take a simple example. Imagine a program that writes data to a file in a loop. If the user presses Ctrl+C, the program would normally terminate immediately. But what if we want the program to first close the file properly and print a message saying goodbye? In this case, the program can install a signal handler for SIGINT. When SIGINT arrives, the handler runs, closes the file, prints the message, and then exits gracefully. This idea is very important in real-world applications. Many server programs rely heavily on signal handling. For instance, a web server might run for months. When the system administrator wants to stop it, they send SIGTERM. The server catches SIGTERM, stops accepting new connections, finishes handling current requests, saves logs, and then exits. Without signal handling, the server might shut down abruptly and lose data. Signals are asynchronous by nature. This means they can arrive at almost any time. A process does not know exactly when a signal will be delivered. This makes signal handling tricky. The code inside a signal handler must be very careful. It should do minimal work and avoid complex operations. This is one reason why signals are used mainly for notifications and control, not for transferring data. It is also important to understand how signals interact with process states. Earlier, we discussed that a process can be running, ready, or waiting. A signal can change the state of a process. For example, a running process that receives SIGSTOP moves to a stop state. A stop process that receives SIGCONT moves back to the ready state. In this way, signals play a direct role in process control. Signals also relate closely to job control in the shell. When you press Ctrl+Z in a terminal, the shell sends SIGTSP to the foreground process. This stops the process and puts it in the background. Later, you can resume it using commands like FG or BG, which internally send SIGCONT. So even interactive shell behavior is built on top of signals. To sum it up, signals in Unix and Linux are a lightweight but powerful communication mechanism. They allow the operating system and processes to notify each other about important events. They are not meant for data exchange like pipes or shared memory. Instead, they are meant for control, errors, and lifecycle management of processes. Understanding signals gives you a clearer picture of how the operating system maintains control while still allowing processes to react intelligently. As we move forward to topics like process creation, termination, and zombie processes, you will see signals appearing again and again as a core tool used by the operating system to manage process behavior. That is it for this video. See you in the next one.